Thanks, Peter. I was thinking this morning, why did I do this to myself? But yeah, so here we go. I'm going to talk a bit about R&D results and into optimal process design. And why I'm doing this is it's actually tie on to what Jacques mentioned this morning, is that where you sometimes tend to look at data and use that in design, and also take data and take it on face value and say, okay, this is going to be the best outcome. So I'm just trying to explain a few things to you as I go along and give you a bit of a case study just to give you an example. I'll give you an introduction, talk about some issues, mistakes we make, give you a case study, and then we'll go to conclusions and acknowledgements. So for every 1,000 prospects, there's about 100 that are drilled. 10 really become a project, and 1 become a mine. Well, Brock said that in 1985, and it haven't really changed, to be honest with you. Each ore is unique, and no 2 ore deposits are the same. And I think if you design and you do greenfields and brownfields, you have to realize that that is a very important factor to remember. And if you don't do that, you're actually already halfway down the track on the wrong way. So to manage technical risk, in metallurgical flow sheet development, there's a few things. You can minimize those risks via some test work. You can effective flow sheet development during various study phases, and I'm not an advocate to say that you have to go through each study phase. It depends on your accuracy of what is it. You get people who go from what they call a PFS to a detailed design, but that PFS might be at a 20% accuracy or 18% accuracy. Look at the accuracy and look at what they've done at that stage. But we also seen PFSs at 30%, and people go into detailed design. So that's again a risk factor inside. So if you're going through the various study phases, you would actually go through most of these issues that you can minimize risk. Project risk assessment as you go along. If you do things, add that to a risk assessment. A good example is if I go to any place, I'll usually ask them, what's the PDC? Now then they say the PDC has been done 6 years ago. We've been in operation 6 years ago. And I still say, okay, have you changed anything? No. So what's the PDC? That's your last baseline. Okay, so how did we change as we've gone along in the 6 years? Because interesting in the studies and in design, the PDC is actually the design basis of what you're doing design on. And the PDC has got an interesting little column on the right. And the column on the right say, where did you get it from? Usually it's from calculations, modeling, test work. But there's 2 really interesting little abbreviations as well. One is engineering company or client knowledge. The other one is professional knowledge of the engineer, and nothing wrong with those. But I will explain today that even with test work knowledge, that you even say it's from test work, you can make the wrong decision sometimes, and that's important. So just look at process engineering risk and the area of problem. And it's an interesting thing to look at, that mine design and scheduling is still the highest, and I mean it's out there. But then if you look at the number 3 and 4, which is metallurgical test work, and the process design and selection, you can see that 27, you're getting to a third. A third of risk is still in a process flow sheet and the test work, the 2 combined. So it's not far away from your mine design and scheduling issues. So that's an important factor to realize. So what issues should we consider in process design? There are numerous examples of projects that failed. Often poor process performances can be attributed to the use of inadequate or poor or unusable or unstable or unsuitable metadata during various phases. So things that we have to look at is the sample and the test work program, and just some examples. The paper gives much more information, so go and have a look at it. But I've seen studies at the sometimes DFS levels that still have sometimes RC drilling and composite test work in there. Now, if your ore body is very homogeneous and you can prove that that's going to be the case, it might not be an issue. But really think about what you're using for what level of accuracy and what level of test work you go. So you can see there's some type of examples. Grab samples, we don't usually as metallurgists or chemical engineers like them. Maybe in a scoping study, it's fine, you know. RC drillings as well. A small diameter, they can be better, but we tend to like large diameter stuff and even bulk if you can go that way at that level. So that's the information. So it gives the guys who are doing the work a bit more confidence in what they're doing. So what other issues is there? There are issues as analyzing the data. It's a tool. So in the paper, there's a lot of tests that you can do. There's a table 3 that I've got in there that it gives you all the types of test work and various stages of the project which you can do or should be considered. The impact of proposed changes. So things that can really be important there is product purity, process safety, CAPEX and OPEX. What's that impact of those proposed changes on your design? Metallurgical accounting, how effective will that be? Cost savings. Test work is expensive. So people will say, I'm not going to spend another maybe $100,000 on getting you another few comminution tests done. It's very expensive, but if you think about the comminution circuit, it's probably going to be more than a third of your CAPEX, if not lower, and that's a massive amount of money you're actually giving out on that circuit. So be careful that cost savings in test work programs can actually cause you to make wrong decisions. Understanding the properties and limitations of equipment, it's an important thing. I mean, we here at this conference, and you can go to the exhibition, there's various equipment you can use. I mean, you've got different concentrators, you get a Falcon and a Nelson, you get different leach tanks, they're all good, but some of them is more applicable to certain situations and places. Jacques was mentioning it this morning, it was excellent. If you're doing a design in a third world country, think of what equipment you're going to use. Think of the complexity there and the people is operating in maybe water or come and servicing the equipment, etc. So that's an important factor, you know, that you have to consider in that. Understanding your relationships, and that's a very important one. If you don't understand your relationships in your ore body or minerals processing or the geometallurgical relationships or things like that, you don't really understand what you're actually looking at. So that's a very important factor. So if you look at data, what do you do with data? I mean, there's various ways. We get multivariate statistical methods we can do with data, steady state models, where you actually look at a mass and energy balance, but their change over time is ignored. Then you get dynamic models where there's a bit of an influence of time. There's various ways you can look at data. Choose the right method. I mean, Chris Aldrich always said to me, and he was a guy, and then he was starting with artificial intelligence, all these things, and I said, Chris, what's this? And he said, they are just tools. But if you don't understand what they can do, you can't actually analyze the result. So be careful if you give data to people who just plug it into a tool, give you results. If they don't understand what that tool is doing, because some of his statistical methods and tools can't be applied to certain data sets due to noise and a lot of other things. So be careful who you use and what you do with those information. I mean, you can, with data, your information, it gives you knowledge, it applies, and you can take it through circuit. But I mean, there's just a normal relationship model. Sometimes you get data which just gives you a relationship. And that relationship can be so accurate and good that you can use it. Even in geometallurgical models, you can use it in various things. You don't always have to go to statistical or dynamic models. Sometimes it's just a relation. They're not always there. Then you have to be careful. You have to go and look what's other ways to go and use it for. So I mean, just in greenfields and brownfields, sometimes modeling have a different approach. And I just thought I'll show this here. That, you know, in greenfields and brownfields operations, you basically will effective test work design, you ensure test work results reflect the actual results, the variability. You do preliminary process modeling, statistical analysis, that's the type of thing. But in established processing operations, what do? There's a lot of data available, so it's data mining. We talk about what you can do with data. You can do process optimization, and you can do reconciliation. So there's a lot of information available already on site, especially if you expand or change. Go and look what you got, but also realize that there's a lot of issues with that data, and you have to be careful how you use it. So what other issues? Other issues is identify the best process flow sheet. Not always the most commonly one used. And I think this morning, both speakers spoke about that as well. You can start from that baseline. Everybody have to, I'm a very strong believer in just start from a baseline. Start from something you can stand on and you know its effect. You can start from that baseline, but it's not always the best for you. Okay? So don't think because your neighbor is using it, it's going to be the best for you. Economies of scale. What your neighbor is doing at 2.5 million tons throughput and you might have a 1 million ton of throughput is different. It's not to say that the same process plant is going to work for you and the same equipment he's using or she's using or they're using is going to work for you. Sometimes also look at your preferred flow sheet, protected by some patent and issues, IP issues. In the gold mining, it's less issue, but nowadays, with the new Lexivians Jacques was talking about, there's some IP issues. Make sure you understand those issues. But basically, in the base metal industry, there's a lot of those issues that you have to be careful. The guys will tell you they've done the test work over the last 5 years, 7 years, and then suddenly, if somebody go and do a bit of an IP search, you'll see that BHP or Rio owns half the IP very close to that, and it's very difficult then to actually convince. You have to go through a long process, so be careful. So do not always ask where else is this technology applied. That can be a major drawback. Just think a bit outside the box as well. So what mistakes do we make? We usually rely on use of similar or previous test work, or test work from neighboring assets. I mean, I've seen people come and say, oh, this is exactly the same as the guys next door. This is some test work they've done, so it should apply to us as well. You know, or previous test work done 10 years ago with old equipment, etc. They're valuable. Have them around, use them. But don't rely on them totally. You don't sometimes even know how that they selected the sample. Was it a snapshot? A lot of test work is a snapshot. You took a photo, and the time is gone. Is that photo exactly the same as you're going to see in the next few years? You have to be careful about that. So be careful about things like that. Scale of test work. I mean, if you just want a scoping study cost estimation at an accuracy of 35, 40%, you just want to see, is this worth putting money in and going a bit further? You don't need massive amount of test work. You need a few pieces of test work that you can roughly rely on. You can make assumptions on those. But as you go along the study, you need to realize that if you the test work that you're doing is, for example, still based on some of those initial assumptions, you're going to totally go the wrong way. So be careful in that regard. So if you look at that just quickly, some of this, you know, you'll just this is just what you call it, a guideline. It's not the law. But I mean, when you get to bankable, full and detailed design, there's a lot of things had to be done by that time, and you have to be comfortable. Now, the engineering firm, and that's an important one, and I want to, just before I do the case study, and I've got 6 minutes to do it, sorry, is the engineering firm usually will tell you in that regard, for example, you know, he needs to realize that if he gives you a 20% or 15%, he say to you, this is a 15% study. So I'm putting my head on the block that this is 15% in CAPEX and OPEX. You have to be comfortable that the test work and process flow sheet design, everything is, it covers the whole ore body, it covers the variables, it covers all those. If it's not doing that, even if he tells you it's 15%, he's lying to you or she's lying to you. Be careful. Look at what they assumed from. I've recently saw one, to be honest with you, I do a lot of due diligence work, and I recently saw one in the chemical industry, more chemical process, where 80% of the PDC was assumed, and it was at a 15% accuracy by an engineering company. And to be honest, it's not owned by that engineering company, it's actually owned by the company, the client, but they work together, but it tells you a lot Okay, so be careful. Right, let's just quickly look at an example. We have a comminution circuit. It's a milling circuit upgrade. It's an existing operation. They want to upgrade their milling circuit. They want to put more through. They have been running for a long time. There's a lot of plant data available. Evaluations based on incremental costs. So they want to see what's operating. So we've done a bit of a financial analysis. So just interesting. They took some 4 samples, duplicated it, went to the labs, done a real nice grind sensitivity, and this is what they got. So they got 4 points. So basically they got 4 points, various grinds, various recoveries. Nice little line through it, looks very good. Okay. So then you go on, you say, okay, let's look at the plant data for the last year. Because they got that same material going through the plant, right? Now, sorry, let's go back one. Right, so if you look at the plant data, a bit of a dog's breakfast there. You can put any line through there, I can tell you. So, but what it tells you is that if I look at that, and even if I look at the tail grades, it tells me, first of all, it's probably not great, grind sensitive, to be honest with you. You know, it's all over the place in that regard. There's some other issues there, a lot of issues. So that's their 2 sets of data. They want a mill expansion. That's the 2 sets. How are we going to design? So if you we have a little model which we put in, and you put in things like the revenue benefit, the mill circuit powered, grinding media, just the rough things at the high level to see if it's economic viable, what's the best grind. But then you need to put the right relationship in. Okay. Now if you look at that, this line to the left is a relationship based on the lab test work. That one is based on the plant data. It's totally 2 different relationships. Gives you different optimum grind sizes. Okay? So which one do you select? Or do you select any one of those? This one say at 180 it's the best value for money. This one tells you no, you can go down to 125, even lower. So what's the observation? Data selection, verification, confidence. The laboratory tests have limitations. That lab test works. 1 domain used, 4 samples, split. Is that enough? The plant data has limitations. What's the limitations? Timing, the accuracy of the measurements. Inherent average hides variability. You understand? So what do you do? So just try to say, so in essence, unfortunately, if you put 10 metallurgists together, what will they do? Half will say the lab test is better, other will say no, the plant test is better, etc. So the relatively simple evaluations show that trend and shape of recovery curves are of utmost importance. The confidence in the data and representativity is of utmost importance. And the plant data is a case are slightly more reliable than laboratory data. However, it's not really reliable at all still. But it's at least more reliable because over time, and you can do a few years back, it shows you that that ore body is really not that grind sensitive. But the lab test work shows the total opposite. So what do you do? How do you design it? And that's the important question. So what happens sometimes, and what I'm trying to do is to just illustrate that don't go and design something on a set of data. We might have just had 1 set of data, and you use that, and you decide that's the best to do it. Don't try to design at the end of the day, if you have 2 sets, and try to get to agreement which is the best set. In this case, you need more confidence, you need more samples from other areas of that ore body, and then with those samples and that information, you might get a different trend from laboratory data as well, and that might be slightly closer to what they achieved in the plant over the time. But it's just a simple example. I mean, there's a few others which I can show you as well, which have different trends, but be careful how you use it, what you use. So in conclusion, the grind information depend totally on the quality, confidence, planning and review of the data. How do you do that? And you have to understand the gaps and go back to, if it's not good enough, say, go back, get something else. We need to go and do the test work and get the real data. And if you get the real data, you can sit down and then make some calls. These are good guidelines, but they're not good enough to make actually a call on what you're going to do. Because it's existing operation, you can use, say, the risk is less because this, and if you do this. But at the end of the day, if you choose a certain grind size and you put the power in, it's going to cost you money. And that's a very important point. Thank you very much.
Thanks, Leon.
People have been trying to do this for years, many years. There's nothing else like it.
We're at the beginning of something that could potentially be huge, not just in Indonesia, but worldwide.
We called the company Green Gold for a good reason. A lot of our business is to do with gold and silver projects. That's the economic element to this. But the green part of it is environmental.
Green Gold has a few technologies that we've been able to develop in-house. One of them is resin technology, which effectively uses resin to recover cyanide, copper, gold, silver.
Rather than spending money destroying cyanide to detox it, the challenge has been to recover it and recycle it economically. So the technology we have has now overcome that problem. It is quite revolutionary.
When you make a process that doesn't actually cost the client money, it actually can potentially make you money while still being good for the environment. You know, that's where the real value is for the clients now.
We're trying to provide a total solution to project development. A consultancy, but it's a different sort of consultancy because it's a full package. We provide more than just engineering. We also provide the latest technology. We provide the latest equipment for a mining project. We provide concepts outside of the process plant that help the project, that really is giving the client the best chance of having a feasible project. We have to understand the geology first, and then you can work out what are we trying to mine, what are we trying to treat. And those are the key things we need to understand, and that's why we take this integrated approach.
So the advantage of our team is that we have all disciplines under one roof, so we're able to get quick responses between each of the different disciplines. We're able to eliminate any communication issues, and if there are any issues, we can deal with them straight away. We use Hexagon, a smart plant. The benefit of that is that we are able to give the client value from a scheduling point of view, and time is key, but also we're able to save on man hours and cost. All these units, it's all integrated. So I can make a change to any one of those phases and everything else is updated so that our engineers and designers can focus on what's most important.
What Green Gold's done is put it all in Indonesia. We've taken the expats to Indonesia, the leads of those respective disciplines. We do it here, we fabricate it here through pre-qualified fabricators. That gives us a really easy model to man up or man down. We erect it, we de-erect it, we ship to sites all over the world, and then we'll go to site then to oversee it.
Green Gold is a complete package. We're selling something that's providing the best answer to developing mineral projects. And that's where the satisfaction really comes, believing that we can actually offer something that really is better than anybody else.